Yeah, it's just chaos. Doesn't look like it's symmetric either. That seems to be a problem. Let's see if we can pinpoint it more. Minus 20 seems reasonable. So it is pretty symmetric, at least as far as we can see, and we get some pretty good error. So just this is not the error, it's the exponent of the error. Exponent in base e, so it's like you would have to divide this by approximately 3, I think, or something like that. 3 or 2. Point something, I don't know. To get the real power of 10. So yeah, I think that's what's happening. And this is because, of course, we took a fixed precision here. Took a fixed precision, and so once that precision isn't good enough because you have more and more roots, you know, you need to distinguish them very finely so to keep the symmetry. And that's why you don't see the symmetry, probably. You should test that theory by putting just a few more. I don't know. Don't know what happened there. That doesn't. Let's just compare. See, the degeneracy starts around here, and it's still pretty much around there. I mean, there's also So it does change. You also have to remember that our method for finding the roots isn't super great necessarily. We sort of combine two methods, and it's kind of a but if we keep it reasonable and just pick 'cause I'd say around n equals to 13 maybe, something of that nature. Something around that. So you can start to see it breaking down, but it's still pretty good over here. So say 15. We can keep that. One of the things okay. 10 to the minus 1, minus 2, minus 3, minus 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So there's actually a limit there. Alright. Can't go beyond a certain point, but I don't think we've reached that point. Okay, for this specific case, because we know that the roots are in between 2 points, let's just keep that for now, and write down a simpler version that simply does the bisection method. Let's see what happens. Level A, B, that's all garbage. So that's A. That's B. I think it's still going to work, but it's possible that A is bigger than B in this case. I think it's still going to work though. And just arbitrarily, if we do 100 bisections, we'll end up really close enough. And it's not a big deal because it's not a big deal because if we really care about performance, we can just do this once and then do this for a whole bunch of integrals and it should be fine. If we just do one integral in our program, performance is not an issue anyway. Okay. Maybe. So we don't even check. Just do 100 iterations and that's it. We start with something that's an interval that's not bigger than 1 because, you know, not bigger than 2. You know, we have 100 iterations. Get 2 to the minus 100 times 2, so it's pretty good.